Okay, in this segment we're going to take a look at a conical magnet. So our magnet is going to look like this. Let's put the apex of the magnet at z equals 0, and let's put this flat surface up here at z equals L, and we're going to have a frozen in magnetization M, which is in the constant and in the z hat direction, and the coordinate system we're going to use to analyze this, well, let's put z hat straight up. We'll use cylindrical coordinates, so we'll have a rho hat vector, and our cylindrical angle coordinate will go around in this direction. Okay, so with the z-axis, of course, we'll put the z-axis will be on the symmetry axis of the cone. And let's calculate the magnetic field right at this apex point right here. Okay, so it may well be that this problem is going to be somewhat problematic because of the very sharp, or the infinitely sharp end of the cone that we put here. We'll find that out as we progress through the problem. I haven't done this one, so let's just take a look at how that works. We're going to need the surface normal. Let's call that n hat. We'll put that here, and our strategy is going to be to calculate. We'll break the cone up into circular rings, and we'll calculate the contribution to the magnetic field at this point here due to a ring located at position Z, and then we'll integrate up all those rings. Now I'd just like to point out that the curl of M, the curl of the magnetization, is 0, and so there are no volume bound currents. We only have surface bound currents, K, and those are going to be M cross N. So that's what we'll calculate straight away. Let's calculate the surface bound currents and take a look at those. Actually, before we do that, let's write down our formula for the magnetic field. Let's do that first. Okay, so this is going to be the basic formula that we're going to work with. And this is the magnetic field, or the contribution to the field, the contribution dB due to a current element di flowing around a circular loop of radius r, and as I said, r is a function of the position z. So we're going to need di, we're going to need r squared of z, and that is about it, isn't it? So to get di, we're going to need k, the surface current density, so let's get that first. And to get this, we're going to need the surface normal. I'm just going to write it down. Okay, now if you're in any doubt about how to write this down, just looking at the geometry, you need to go back and look at some earlier lectures or some earlier problems, and if you're still in doubt, you need to come and talk to us, because this is a very common step, and you need to understand how to do this. Let's see, M is in the Z direction, so when we take the cross product, the only piece that is going to matter is the Z hat cross rho hat bit, and that's going to give us a phi hat turn. So let's just write that out without any further ado. Let's just say that K then is equal to M cos theta 0 phi hat. Okay, so there's K, and that's going to be an important intermediate result for us. Okay, so what we actually need is not M, we need di, and to get a current element, we're going to need to multiply it by a length, and that length is going to be the width of the ring that we're considering. So let's go back to the geometry of our cone. Okay, so there's our ring, and we need the width of that ring measured along the conical surface. I'm going to call that dl, and I'd like to relate that dl to dz because I'm going to use z as the integration variable. So I need to know what is dl in terms of dz, the displacement along this symmetry axis, and we can do that just from geometry. Okay, so clearly then we have dl divided by dz is the cosine of theta 0. So in other words, how do we do this now? I have that wrong, don't I? It should be, what should this be? This should be, let's get that right. This should be dz divided by dl. And so I get dl Okay, so let's combine this result then with our previous result for K to generate the current element di. Okay, so this is then going to give us, let's see, what does that give us? This is going to give us okay, so there's our result for di. And at this point we're nearly done. We only have one last job to do, and that last job to do is that is to write down the radius of the ring as a function of its position z. So let's go back to our cone. So here's the radius of a ring. I'm going to call that r of z, and this here is its z position, and this angle in here of course is our theta 0, and once again we can just use geometry to write down the following expression. It's going to be the tangent of the angle, isn't it? So r is a function of z divided by z is the tangent of the angle theta 0. And of course we can now write r of z in terms of z. So that's again an important intermediate step. Okay, so let's put all this together and let's see what we get. So if we substitute those results back into our equation for dB, we get the following results. All right, now I'm going to factor out, what shall I factor out? I'm going to factor a z squared. Pardon me, that's a z squared there. That can't be a 1, it would be dimensionally wrong. I'm going to factor a z squared outside of this this bracket, and then I'm going to divide through. I'm going to cancel a z squared with a, actually I'll get a z cubed outside, won't I? So that'll give me a z downstairs. So let's do that. Okay, so there's our result, and we're actually nearly done because the only thing we have to do now is integrate out over all the rings, and just about the only thing that with any z dependence is the 1 on 2z downstairs. Everything else is a constant. So let's write down the final integral that we're going to need to do. Okay, so there in integral form is our result. And if you take a look at this, we do indeed have a problem at z equals 0, don't we? So the integral of dz on z is log z. And if we try to take the logarithm of 0, where the whole thing is going to diverge. So let's fix that up. How would we fix that up? If instead of integrating all the way down to the tip of the cone, we were to cut the cone off somewhere, really at any point which removes or I should say at any value for z which removes the point of the cone, then our integrals are going to converge. So let's say we're still interested in the magnetic field here at z equals 0, but we're going to cut the cone off, or we're going to cut the cone off at this point z equals a, some non-zero number, and so we're going to integrate to z equals L, and this lower bound then becomes an A, and of course now our integral converges, and our final result for B in this case will be the following. Okay, and there is our result for the magnetic field at the tip of the cone, with the caveat that we've had to chop the chop the cone off just a little bit, otherwise our whole integral diverges. Now, this shouldn't concern you. There are no such things as infinitely sharp cones in nature, and so the fact that it diverged for an infinitely sharp cone is really not a problem.